Okay then, so it's my pleasure to introduce Peter Kirwan, who worked for 7 years at the PhD, came here to be a PhD student, and during the COVID period, he did very important work on COVID, and then after his PhD, he stayed here, fortunately, to work as a postdoc, and he's talking today about the work he's doing now on HIV. Well, he's looking slightly. He's looking as though he doesn't agree with me. So let's just wait and find out what he's going to do.
Thanks everybody for coming along. Thank you, Sean, for the introduction. So I'm going to be talking mostly about the work I did in my PhD, actually, which did involve HIV, and then at the end a little bit about what I've currently been working on with Danny and Anne and others in the group as well. So this was the title of my PhD. Multi-responding estimate infectious disease burden. It's nice and broad so that it can encompass all infectious diseases, which you will see became necessary after I started my PhD in 2019, imagining I would stay focused on HIV for 3 or 4 years, and then COVID came along. This is a collaboration, as all our work always is, but just at the start. So people in the unit, my supervisors, Anne, Paul and Danny, Chris Jackson, who did things today, and Sean as well, who kind of advised me during the 4 years, as well as colleagues from the UK Health Security Agency, Public Health Scotland, Public Health Agency in Northern Ireland, and Public Health Wales, who all contribute data that we use to understand infectious diseases in the UK. So I'm going to talk a little bit about survival analysis, mostly a recap, probably for most people. Multi-state models, what are they? Why? How do we use them? A couple of slides on kind of the applications that I did as part of my PhD into COVID-19, but then mostly focusing on statistical back calculation, which is a method of kind of going from diagnosis data back to instance of an infection. The developments that I made in terms of accounting for recent infection within HIV, and then a discussion. So survival analysis, not as I first thought when I got here, anything to do with Ramirez at all. Instead, this is probably a much better book if you want to understand survival analysis. David Collette's Modelling Survival Data in Medical Research. So what do we mean when we talk about survival analysis? Well, it's the analysis of survival data. So we have to then define what survival data is. So survival data is going to be any time to event data. Very basic terms, an event would be an outcome of interest, and the time is the duration from an origin to that event taking place. So a very simple figure here. This is probably too basic really, but we've got an origin, we've got an event, and we've got the time that takes place somewhere in between. So some examples that we might look at in infectious disease studies are from, say, a study recruitment to an infection occurring, from hospitalization to discharge, from infection to death. So these are some kind of examples. And you might be thinking, wow, this seems really simple. Why is he telling me all about this? Well, some complications arise when we actually look at real world data, as always. But particularly for survival data, there's a lot of complications that typically come up. So these are typically censoring. And this can occur when we have incomplete or unobserved information in our data. So here on the top row, this is what we'd like. Everything is perfectly observed, no censoring at all. What will commonly happen is if we have a censoring window, so here between a sort of a left censoring point and a right censoring point, if somebody's outcome is not observed, then those people are, that information is right censored. And conversely, if the origin is not observed, then those people are left censored. And particularly with some of the administrative data sets that we use, we can get administrative censoring where somebody's imposed a cutoff and we don't have any information after that point. There might be an event that happens, but we just never get told about it. We could also impose that administrative censoring ourselves, of course. The other common aspect of survival data is called truncation. It's kind of a close cousin to censoring, but in this case, we just have no information at all. So in some cases, of course, as before, the time to event was observed, but in other cases, we have these truncation windows, things that happen after, where we're no longer collecting data, we don't know about those. Those are right truncated. Things that happen before the study starts, we also don't know about those things. They might be left. These can all bias our observations, of course. So everything that we need to take into account when we're using survival methods and applying them to time to event data in real world studies. So how can we deal with this? Typically, the two things that we'll want to estimate with censored or truncated survival data are the survivor function. So this is just the probability that you survive for a certain period of time. This can be very simply estimated using the Kaplan-Meier estimator, the very classic that we've all used. So here, this plot on the right-hand side showing kind of a difference between two groups, maybe a low-risk group and a high-risk group, where the high-risk group has a lower survival. The other way we might use survival data is to estimate hazards. So the hazard function, which is shown here, can be estimated using typically or commonly a proportional hazards model, where we have some baseline group. We adjust perhaps for some other covariates, and then we estimate the proportional hazards for another type of group, another person with covariates. So in this case, we've looked at vaccination, the effect of vaccination, and how that changes your hazard of infection. All well and good until we get to competing risks, which make us have to rethink again. So competing risks actually violate the assumptions that we use when we're dealing with time to event data, because they're no longer independent times to events. People, if we're previously were looking at time from hospital to discharge, and somebody gets admitted to ICU and we no longer have any information about them, then obviously the hospital to discharge is not reflective of the population who've been admitted to hospital. We need to somehow account for that. Similarly, somebody might die, and depending on how we deal with that information, that can change whether our analyses might be biased. So there's a number of competing risks, survival methods which are used. I'm not going to go into too much detail, but essentially these are kind of analogues of the Kaplan-Meier hazards that I showed earlier. But in these cases, we're estimating slightly different quantities. So previously we were estimating hazards, and with a fine and grey model, we're estimating sub-distribution hazards, which there's a subtle difference there, so important to understand. Fantastic. So multi-state model, we've got all this fantastic survival information. What are multi-state models? Why do we need them actually? And how are we going to deal with them? One book I'd recommend, which was very useful as I was going through my PhD, was this by Ade van den Hout, who I think maybe spent some time in the unit as well a few years back. So if you want to learn more, I'm just going to give a flavour today. But yeah, why won't we want to use multi-state models? Well, if our disease processes are much more complex, and particularly if intermediate events might change somebody's final outcome, then those standard survival methods that we looked at before might actually be insufficient to capture all of the different processes, all of the different pathways that are going on. So we might have a better chance of understanding our entire method, our entire model, by using something that captures all the dynamics of the system at once. So this is where multi-state models come in. This kind of almond-shaped figure was one of the hospital pathway models which I used during my PhD. So this was some COVID data that was collected, sort of administrative data sets, and we had people admitted to hospital having acquired COVID. And then we were trying to understand the different pathways through hospital, the lengths of stay that somebody might remain in hospital, the chances of going to ICUs, and then the different risks of discharge and death, depending on their specific covariates and their specific age, comorbidity, gender, ethnicity, that kind of thing. Very simply, multi-state models allow us to look at transitions between states. So if we consider two states, R and S, on the left-hand side there, you can see we're just plotting as somebody moves along at a given time T1, they might move from state R to state S. At a later time, they maybe move back. And then at another time T2, again, they move from state R to state S. We can plot this as I've done on the right-hand side, or maybe we want to show it as a counting process. So if we want to count the number of times somebody moves from R to S, that could be called a counting process. And in that case, we might plot our transitions like this. And more commonly, we're going to represent the transitions between these states using a diagram. So again, this is kind of showing a very similar, same thing really. We've got state R and state S. The arrows that connect those are called transition intensities. So the transition intensity from moving from state R to state S, I've labeled here QRS. Then we've got the reverse transition, and somebody can stay in a given state with a specific transition as well. So how can we, what are we going to do with these information? So typically we're going to form a transition intensity matrix. This is this Q, capital Q, on the right-hand side here, which contains our transition intensities. And you can see actually what I've done is show that the transition intensity for remaining in state R is equal to the minus transition intensity for moving out of state R. And similarly, the transition intensity for staying in state S is the minus of moving out of state S. And if we had more states, maybe explain a little bit clearer here, but essentially we sum over all of the states, and then the transition intensity for remaining in the state is sort of the negative sum of all of the transitions out of the states. A bit more formally put, then, the transition intensity is the instantaneous risk of moving from one state to another, or else the probability as delta t tends to 0, that the net state will be state S, given the current state is state R, all over delta t. We have some nice convenient properties when we're talking about transition probabilities and transition intensities. So probabilities over a time period can be estimated using an exponential function. It's a very convenient property of these multi-state models, particularly Markov multi-state models, although that assumption can be relaxed. And then another convenient property is the sojourn time, which is estimated as the expected time to spend in the state. And this is the reciprocal, so 1 over the transition intensity for staying in the state. Sense? So why, another reason we might want to use these models is that they're particularly useful for investigating intermittently observed or interval censored data. This is sometimes called panel data. So where we're observing somebody not continuously, but at certain follow-up appointments. In hospital, you might test someone every 2 weeks, or they might have an appointment every month. And that information can be translated into our multi-state models, and we can still obtain unbiased estimates using these models, even if the observation or the follow-up is even less regular. So it might even be so regular that we miss a change of state, but as long as our observations are what was called non-informative, then the multi-state models can correctly account for this intermittent observation. So that's a very nice progress. Awesome. So the last thing I'm going to talk through, again, this is just to give you a flavour, and then I'm going to talk about some of the applications. So the multi-state models, when we're using them, they're very flexible. We can include covariates on different aspects of the model, so different transitions. We might want to include different covariates on, that's absolutely fine. And when we are wanting to estimate parameters of the model, we can fit it to data using likelihoods, simply by taking all of our observed data, the transitions that people make, or essentially the different observations that we have for an individual, and then multiplying over all individuals and all transitions gives us the likelihood for the model. There's some fantastic software available. So Chris Jackson, who works in this unit, develops the MSM and the FlexServe R packages, which are both Quantist packages for modeling R, and just with any sort of Bayesian methods, that is a very good program that we can use for fitting multi-state models in a Bayesian framework. Great. So I said I was going to talk a little bit about COVID-19. When this came along, as some of you were here and remember that the whole unit kind of changed focus for a few years, particularly in the population health theme. It was important that we could work with UK Health Security Agency or Public Health England, as they were at the time, and assist them with kind of understanding this new infection. Even basic things we didn't really know very much data about. And right at the start, we were looking at Diamond Princess data from the cruise ship, trying to understand the risks of this new infection, which no one had any exposure to at all. One of the first projects I got involved with was estimating hospitalized severity. So that, remember that almond plot, I call it an almond plot that I showed before. So here we were trying to estimate different pathways through hospital, the risks of different outcomes both before and after vaccine introduction. And a couple of years ago, we published a paper where we kind of presented the results from this research. You can see here, this is the risk of death, discharge, and ICU admission by age group, and how this changes over time. So in this particular plot, we were investigating whether there was much seasonality in COVID-19 by fitting both the kind of seasonal circling model as well as the month-by-month risks. So that's that piece of work, which was looking at in-hospital. I then subsequently worked on a study with healthcare workers, so where we were looking at the effects of vaccination and of prior infection on somebody's future risk of getting infected with COVID-19. So this was a study set up by colleagues at UK Health Security Agency, where they recruited about 50,000 healthcare workers who volunteered, which I'm amazed at, to swab themselves every 2 weeks, and filled in a questionnaire as well, telling us about their symptoms. We were able to fit a much simpler model, as you can tell, so just susceptible and infected components. But the complication here was that we were fitting a much larger number of covariates within this model. So obviously we had lots of information about the people's age, gender, where they worked in the hospital, what kind of vaccination they'd encountered before, all of this fortnightly data. And for 50,000 people, imagine you times that by fortnightly tests over 2 or 3 years, we're crunching a lot of information there. Our most recent piece of work on this just came out last month in the Journal of Infection. And here we were looking at the estimated booster vaccine effectiveness. This is kind of overall, depending on whether somebody's had a prior infection within the past, not 6 months, 6 to 12 months, 1 to 2 years, or two or more years. So you can see the effect with booster vaccination is greater for people who've had a longer time since their last infection. And we also split this. It was quite nice in 2023 would be now, so a year ago, when the booster vaccines were given. Some people got the bivalent original and BA.4/5 formulation, and other people got the monovalent XBB vaccination, which was the circulating variant at the time. And we found that the vaccine that had been formulated to the circulating variant was much more effective at preventing people from getting infected, even though we've got quite wide confidence intervals here. And that's informed the recent vaccine. So the rest of the presentation, I'm going to be talking about statistical back calculation. I've made a distinction here about statistical back calculation, because if you search back calculation on Google, then you get this plot comes up about pavement structure. So I mean, you may know more about me than this, but we're not talking about this today. We're going to talk about statistical back calculation. What's the idea behind this? So following infection, and this could be any general infection, an individual can remain asymptomatic for some time. And if we don't have a test, we're not able to test them, then we have to wait until they present with symptoms, and then we can form a diagnosis. So in this case, as you can see, the symptoms, the symptomatic diagnoses, which is the black line, kind of lagging behind the incidence, which takes place earlier. And we might not even see the same shape. It kind of depends on how much lag there is, what the distribution is after somebody acquired their infection to the point at which they get diagnosed, and present with symptoms. So we can make some assumptions. And here we might assume that the time of someone's symptom onset is equal to the time of their exposure plus some incubation period. That's fairly non-controversial. And this can be expressed in continuous time by saying that observed diagnoses at time t are kind of an integral over people who acquired their infection at time s less than t, multiplied by the equation distribution from time s to time. So people who acquired their infection a long time ago, who have a long incubation distribution, might be diagnosed at the same time as people who acquired their infection recently, but only have a short infection distribution. So when we're looking at diagnoses, they're going to be a mix with different times of infection and different lengths of incubation. And so what we really want to do is reconstruct from the diagnosis data, which we observe, what our incidence looks like. And this is called back calculation. And that can be applied to lots of different infections. Typically, for things like COVID, for flu, then your infection occurs. And then quite soon after, you start exhibiting symptoms, so maybe 1 or 2 days. For infections like HIV, the time at which you remain asymptomatic can be much longer. And so back calculation has been used for many years in the UK to understand what's going on with incidence in our population, based on diagnosis data, which might be kind of several years lagged behind. It's up to 5 or 6 years from infection with HIV until someone presents with AIDS symptoms. But of course, with HIV diagnoses and HIV testing being available, then people can be diagnosed earlier. So what's been done in the past is to try and understand all of these different contributions and how they relate to diagnoses that we see now, how we map back calculate. So everyone loves a pie chart. At least the National AIDS Trust love a pie chart. This is just a nice plot showing that the concentration of the epidemic in the UK is with gay, bisexual, and other men who have sex with men, and heterosexual men and women is primarily a sexually transmitted infection. And in the UK, those heterosexual men and women tend to be people who come from Black African background. Historically, that has all been people who've migrated to the UK from very high prevalence countries, although increasingly there is some, there's a mix of incidents happening within the country and people who acquire the infection outside the country and moved into the UK. Because of that complication in terms of migration, the majority of the work that's been done on incidence estimation in the UK is focused on gay and bisexual men, because we've got a much better understanding of where those people acquire their infections, which is in the UK primarily. And it's also a group which has a very high risk of HIV acquisition still compared to sexual men and women, and even as white sexual. You can see there's a small numbers of injecting drug users, vertical transmission and other. So again, yeah, that's why we're primarily focusing on sex between men. What information do we have at HIV diagnosis then that can inform what we're going to estimate? So one of the markers that's collected is called a CD4 count. A CD4 count is a measure of your immune functioning. There's other counts, the CD8 counts as well. So this is just a standard one which is collected for people living with HIV. You ignore this side for now, then we've got a really nice relationship between CD4 count and time since infection. So that relationship can be used to infer how long somebody's been living with their infection. Then we can use that back calculation algorithm and reconstruct what must have happened in terms of incidence to observe diagnoses at different CD4 counts as we see them. I'm saying ignore the left-hand side as well, because that's only the first 12 weeks. And historically, HIV tests haven't been very sensitive in those first 12 weeks. So the likelihood that somebody would have been picked up at that point is quite low. So we've been using CD4 counts for a long time. And fittingly, the name of the model, which I'm going to describe, is called the CD4 back calculation. It's a discrete time Bayesian multi-state model. And in discrete time, we assume a kind of a quarterly basis for the diagnoses. That is a simplification in some ways, but it also kind of fits with the way that HIV infection, HIV instance, HIV diagnosis data is collected on a quarterly time scale. So we can model the infections according to a Poisson process. In this case, it's a time varying Poisson process. with rate lambda t. And we're going to steadily build up that multi-state model. So we've just got the HJ coming in on the left-hand side, representing infections. We can then use that CD4 count information and think about people with an undiagnosed infection living with HIV, and they might be at different stages of their HIV progression whilst they're living with HIV in the country. If we were to test them, then we'd see that their CD4 counts were at different levels. So we can split those CD4 counts into different groups. We've got quite coarse splits here. CD4 counts can vary quite a lot, even day to day, even depending on what food you've eaten for lunch, if you get tested in the morning or the evening. So these models use necessarily quite broad scale, ranges in terms of CD4 counts. But generally, starting on the left-hand side, somebody's going to start with a higher CD4 count above 500, and then steadily decline over time according to some progression probabilities, which are the Qs in this case. So Qs are not time varying. Obviously, as we learn the model and move through this this multi-state model, then we're going to have time varying numbers of people in each of the different states. Of course, if people get all the way through the model and present with symptoms related to AIDS, then we can put them into this AIDS case, this AIDS state, which is a diagnosed state. We assume that everyone who reaches an AIDS symptoms will be diagnosed. But people can also be diagnosed at previous time points, dependent on testing. And as testing rates have changed over time, then these diagnosis probabilities are also time varying. And we have different diagnosis probabilities depending on how far through the CD4 is like. So somebody who's recently acquired their HIV with a high CD4 count, it's a different chance of getting diagnosed than somebody who's been living with HIV for, say, 2 or 3 years. Hopefully that all makes sense. We can talk about the, so you can see that this is a model which is going to evolve over time. So the model dynamics are then going to be based on our transition matrices that I described before. So these are Q, which are QJ, which represent the transition disease progression. And then DJ, which represents the diagnosis. And then at every time step, we also get an addition of new HIV infections. So the next step, I'm just going to term that the sum of these HIV diagnoses at the bottom, I'm going to call mu H. And then these AIDS diagnoses, I'm going to call mu A. Then we can describe how we're going to link this model to the diagnosis data that we see. So just going through this kind of a little bit more carefully. We've already described, so we've assumed that the infections occur according to a Poisson process. And we can decompose a Poisson process into thin Poisson processes. So because our AIDS diagnoses and our HIV diagnoses arise from a Poisson process, they themselves are also Poisson distributed. So we assume that the HIV diagnoses arise from Poisson distributions, and then the CD4 count data is then going to be multinomially distributed with probabilities according to the number of people in each of those CD4 count states at each time. So we can form the likelihood contribution. This is just a standard for a Poisson distribution and for a multinomial distribution. And then our full likelihood is the product of those two terms. Okay, we've got a lot of time points, we've got a lot of states. We can't really fit that model. There's too many parameters going on. So for identifiability and also to kind of smooth out what's happening with infections over time. Then we model the number of new infections and also the diagnosis probabilities as random walks or recently slides or Gaussian processes with priors included on those hyperparameters included on the hyperparameters of the HDs. Either chosen based on previous studies in terms of what you know about what the probability of diagnosis was historically, or assumed about that, or because it's not informative via the same variables. The previous PhD student, this is Francesco Rizzi, who extended that model to an age-dependent setting, where we used 4 different age groups and looked at incidents occurring in each of these different age groups. And you can quite clearly see how incidence is quite distinct from diagnoses, especially or particularly when we're looking at these age groups. So you'd see many more diagnoses in the over 45 group compared to incidence that occurs within that age group. Compared to 15 to 24 is actually the incidence is greater than the number of diagnoses that you'd expect to see. It's not surprising, but in this way we can get quite reasonably accurate estimates of incidence or reasonably close credible incidence. Fantastic. So why do we have an issue with this? That model's working very well, but increasingly people are getting diagnosed earlier. Before I move on to the next part, I need to talk to you about a window period. Some of you might know what a window period is, but I just wanted to define it because it tends to be quite specific to HIV tests because of this time that somebody can be undiagnosed, and also the virus is not immediately present within the system, so it takes a bit of time before a test can pick up that you have a HIV infection. And that time is called a window period. So the time from infection to a positive result. And you can see these differ depending on the different tests. So Western blot was one of the earliest tests that was used. And then we have different generations of tests. The 3rd generation test went back to about 3 weeks. That was just using antibody. 4th generation tests have been able to go a little bit closer to infection by also considering these P24 antigen levels. So the more developed the tests are getting, then the more chance there is that somebody can be picked up early on in their infection. And if you remember back to that figure I showed you, there's much more chance that someone's going to be in this zone when they're diagnosed. And their CD4 count is then going to be quite misleading about how long they've been living with infection. And this is becoming increasingly a problem for epidemiologists. So one of the definitions that's used for tracking HIV diagnoses in this country is called late diagnosis. And that definition was actually updated a few years ago to account for this very issue. And it seemed that this was a larger issue for gay and bisexual men who tend to test more frequently, tend to be more active in terms of accessing gun clinic attendances, getting tested for HIV, and also younger people who are more likely to test. So increased frequency of testing, those more sensitive tests have become a limitation. And then another limitation which I kind of hoped we could address in some ways was the fact that as you get closer to the point at which we do the estimation, then our estimates of HIV incidence get much less precise. This is because we just don't have very much information about people who've acquired their infection in the past few years. That CD4 greater than 500 box that I described is quite, it's a mix of lots of different people. So we have to make quite a few assumptions, and it ends up that we can't make very precise estimates. Compared to if we go back several years, then we do have a much more precise idea of what's going on with the trajectory of HIV infections over time. So the aim for this piece of work was, can we improve our estimation, maybe by incorporating some other information in our model? So I spent a bit of time considering, well, what could we use? So viral load, I've shown you already, that kind of follows an inverse trend to the CD4 counts. There's information maybe on seroconversion. So seroconversion is the time at which the virus is becoming ingrained in your system. And at that time, people can experience symptoms. So those symptoms are quite, you can see actually the window period for the symptoms is quite short. So maybe we could use information about people who get diagnosed during seroconversion to inform that they've recently acquired their infection. We could do the same thing with testing history. If particularly these people who've been diagnosed recently, if they've been testing frequently, we might know something about their previous HIV test. Maybe it's within the past 6 months, say, then we know that person has acquired their infection within a 6-month window. So they're not somebody who's kind of got long-standing HIV. Other information that we might have been able to use was this P24 antigen. As you can see, that's got quite a pronounced period where it comes up and down. But in the end, we decided to go with avidity assays. So avidity is kind of binding strength. So as the virus is infected, as your system learns the virus and the antibodies get better at binding to the virus. So binding strength at the beginning is very weak, and then as immune response develops, the binding strength gets stronger. And we can measure that using an avidity assay, which is also known as a RITA test. So RITA, you may have heard of, stands for recent infection testing algorithm. So it's a way of taking avidity assay results, trying to minimize some of the false recency. We decided to use those because they've got a longer window as well. So the P24 antigen, for example, is only about 3 weeks, where we'd actually be able to use that to reclassify somebody as being a recently acquired infection. Whereas with these avidity assays, we can go up to about 6 months. So somebody who's in the first 6 months of their infection can say that they've already recently acquired. So we had our CD4 back calculation model. We're now going to be using the CD4 and a RITA result or an avidity result. So this is a dual biomarker model. And essentially what we want to do is add in these additional states at the left-hand side of our model. So people are either recently acquired or they go into their non-recent. And if people do acquire their infection at that point, they can also be diagnosed. Because we're working on quarterly timescales, if you remember that. So we previously it was 3-month timescale. We're going to split these latent states in half. So we've got the first 0 to 3 months, and then the next 3 to 6 months, which can both be identified as a recently acquired infection. And then melding this with previous model, it ends up that we need to add actually 3 new latent states, because we wanted to maintain the same possibility for somebody to move from infection through 2 time steps and still end up in this CD4 200 to 350 state, which wouldn't have been possible if we'd forced them to move straight down. We hadn't included this additional state here. So we've got three latent states which can result in a recently acquired HIV infection, and then the rest of the model continues as normal. Right, good question. Does it work? Hopefully. So how can we measure this? One way was to simulate some data and fit both the CD4 only model and the dual biomarker model. So that simulated data. So I simulated some HIV infections and some diagnosis probabilities, propagated those values through the equations that I showed you earlier, and we end up with some simulated data that looks a bit like this. And that can then be translated into diagnoses at different CD4 strata. And so what does it give us when we fit those two models? So I fitted these two models to 500 data sets, and then here just showing the mean fit. So on the left-hand side is the incidence, and you can see that's actually fairly good in both models, which is reassuring. It means that we haven't been systematically incorrectly estimating incidence for 20 years, which is a good thing, because they've been published in kind of annual reports for the UK. But what we might have been doing is overestimating the number of people living with HIV. Of course, again, I've got to reiterate, this is simulated data. So this is just one possibility. But you can see that when we're estimating undiagnosed HIV prevalence, actually the dual biomarker model is much better at estimating that. We can also look at the bias as a performance for what's going on with incidence. So does this actually, is this going to give us a better measure of incidence anyway? So we can do that using bias, also predicted mean squared error. And indeed, on both of those metrics, we see the dual biomarker is slightly better performing than the previous. Okay, the real test is, can we apply this to real world data? So this is for up to the end of 2019. You might say it's a bit of a soft test because we're not considering COVID, but up until the end of 2019 at least, then we do estimate the fairly similar curves in terms of the incidence. Again, on the left-hand side, this is when we're applying it to UK data. And for the undiagnosed prevalence, you can see the difference between the two models, particularly in those earlier years. Although it's starting to come together a bit now, but that's probably just due to the incidence. One thing we can also do is compare with other models. So there's other ways that we can estimate undiagnosed prevalence from HIV data. One of those is called MPES, stands for multi-parameter evidence synthesis. So it's an evidence synthesis model that takes lots of different sources of data and tries to understand the number of people living with undiagnosed HIV, not just gay and bisexual men, but this is across the whole population. And when we compare with those estimates, then we see maybe a slightly better fit with the dual biomarker model in recent years. A bit difficult to say back here, but there's obviously biases in both models. So, at least in recent years, there seems to be a better fit to these MPES estimates. So pretty much most of the talk. So the dual biomarker model, as I've shown you, closer to the simulated values compared to the CD4 only model, and also closer to this MPES model. We're making an effort to make all of the code available for this. So there's a GitHub repository which has the original back calculation model, the age-dependent model, and then both of those kind of extended with this additional recent infection states. And then what I'm currently working on is accounting for migration. So these are data. I haven't actually put a source here. This is data from the ONS on inward migration to the UK over the past 10. Okay. And you can see since 2020, that's been really on an upward climb. And this is definitely going to affect our estimates, particularly the people that are coming into the UK are gay and bisexual men. But also we want to extend the model of incidence to heterosexual populations. Increasingly in the UK, gay and bisexual men are a smaller and smaller group who are at risk for HIV because of things like the testing, which I've shown you, these combination prevention efforts, but also PrEP is now being diagnosed, which you might know is a drug you can take pre-exposure, which stops you from acquiring the infection. And that's got very good uptake among gay and bisexual men, not so much among heterosexual populations or at-risk heterosexual populations. A lot of this migration as well, although the ONS isn't quite giving us what we want in terms of country breakdowns, but much of this increase is among people who are migrating from parts of sub-Saharan Africa or Southern Africa where HIV is endemic. So we would expect that a larger proportion of these people may be going into the UK with already diagnosed HIV or perhaps with an undiagnosed infection as well. So untangling exactly where incidence is taking place from diagnosis data is a key challenge that we want to work on now. This is just kind of a sketch of one way we might want to do it. So rather than just having people enter our model from the left-hand side as incidents, we might have people entering from the top as migrants. In this case, these would be entering into the undiagnosed states, but then we also have at the top, you can see the transfers of care. So we'll just finish by saying the road to PhD is winding, but it's been a good experience being here, and I think having an opportunity to work on lots of different projects during my time as well. And yeah, thank you very much.
Very much, Peter. Questions? David.
Thanks. Do you have an intuition about why it's doing so much better with the undiagnosed prevalence? Is it to do with the bounding of the infection times or some other aspect relative to the old model?
So I think the fact it's doing better is because those people who have previously been assumed to be living with HIV for say 2 or 3 years added to undiagnosed prevalence for those 2 or 3 years being taken out, and they're only accounting for maybe 6 months of undiagnosed infection. So we're kind of getting rid of this.
Excellent. Oh, thank you. I have a question. You commented on this. So you assume that the only, I mean, to reach AIDS, you need the lower count of CD4. Is that a fact, or is it that because I imagine that the test is just different, no? That just to detect the real diagnosis, not AIDS.
It's true. So AIDS diagnosis in this country at least is based on AIDS defining illnesses. There's 23 AIDS defining illnesses. They tend to occur when someone's got some kind of immune system that's been suppressed for a long time. There are some people who progress very quickly. So those kind of probabilities are encapsulated within the model. So in theory, somebody could, with some probability, it's unlikely, but I should have stopped. Okay, somebody could, within 4 time steps, get from here to here.
They need to get there, they could do it much faster.
They could do it faster.
Less than.
In this.
No questions? Check online. One question, just write in the chat. Probably we can say that you have a question and then type it in. And then next time to. But otherwise, so it's almost 3 o'clock, so I think we'll draw it to a conclusion there.